Hello everybody. First of all, I have to say that most of the time we don't need to break crypto. Okay? Why? Because crypto is usually the strongest link in the whole security chain of one product. And you don't really need to break crypto in order to break the product. But yeah, okay, breaking crypto is fun, so I propose to do it together now. I'm going to explain you some. So here is the outline of my talk. First of all, I will just speak some blah blah about crypto and security. Then I will introduce the concept of side channel attacks. So if some of you here are developing secure embedded platforms like smart card or something like that, maybe you are aware with, but it will be quite useful to look at the side channel attacks, which is a kind of special attack. And I have promised the organizer that I will do some live demo, so we'll break something together. Okay, we will look at me breaking something. And I'm gonna to play with what we call padding orator, which is a kind of attack that we can apply against software, not against any platform, not against hardware, but against software. And I'm also going to speak about another kind of side channel attacks against software, which is timing attacks, and I will focus on the operating system. That's the problem. So first, blah blah. Of course, with the apparition of internet and other networks, the use of crypto has literally exploded. So maybe in the 70s or in the 80s, only very few people knew about cryptography, worked with cryptography. There was only people working for the government or the army. But then the internet appeared, and there were networks everywhere, and we needed security. And of course, crypto is one of the networks which can help you bringing security into the project. And fortunately, this guy was there. This guy is he wrote a book which is very famous, which is called Applied Cryptography, which you can still buy in bookshops, although it is rather obsolete now. And this guy saved the world because he explained all of cryptography in a single book, and he described algorithms, protocols, and he even gave some source code to implement this. And basically, yeah, really he saved the world at the beginning, but now it's a bit more complicated. Because if you have a look at the list of the mostly found vulnerabilities in software, and here of such a kind of list edited by the Science Institute, you see that encryption is, or cryptography, the use of cryptography, is one of the frequently encountered problems. So, first of all, you can forget to use cryptography. Forget to encrypt sensitive data, forget to encrypt sensitive credit card numbers in your database, for instance, passwords. You can use hard-coded credentials. What does that mean? It means that basically you have used key which is just hard-coded in your code, and which you can find very easy. You can forget to authenticate stuff, people, processes, and in that case you are vulnerable to spoofing attacks. And more importantly, you can use broken or risky cryptographic algorithms. And that's a bit annoying because now we know that there are good algorithms and bad algorithms. So what is a good algorithm, what is a bad algorithm, is still to be defined. So what might go wrong, Sarah, when you are using crypto as a developer? But first of all, you can badly choose your crypto primitive. Okay? that's the first example I mentioned just one second before. And then here there are a lot of famous examples. I'm just going to mention 3 of them. The Xbox hack, the problem with the web identified. So, once upon a time, Microsoft developers had to secure their Xbox. And they wanted to authenticate the root code of the Xbox, such that nobody can run non-signed code and such that nobody can modify the operating systems. And so they had to find an algorithm, a signing algorithm, which was very small, so which had a very small code footprint. And so I don't know how they choose the algorithm, but I guess they went with Google and they asked, I need a teeny encryption algorithm. Unfortunately, there is such an algorithm, which is called T for teeny encryption algorithm. And they can't. They took it, so it is a very teeny algorithm which needs only very lightweight operation like SOR, additions, and rotation, so you can implement it as embedded software in a very compact way. But basically, it's a block cipher, and block cipher is used to encrypt data, to bring confidentiality to the data. And they decided not to use it as a block cipher, but as a compression function to mount a hash function, to build a hash function, which is then going to hash over the code and to derive a signature using a signature. And so basically, they took a crypto primitive, which is not bad in itself, but they built a new primitive out of it. And the problem is that this algorithm has what we call cryptographers equivalent keys. And an equivalent key, when you are using a block cipher in a hash mode, just means collisions. And this guy here figured out it's a buddy, the guy who wrote the code for the first time. He figured out this very quickly, and he found that by just flipping a bit, you have a collision, so the same hash value, and then he was able to jump the code in an address, the memory, where he was able to put his own code. And that's how we built the existence. And it was really a bad choice of primitive. Another very, very famous bad choice of primitive is RC4, the RC4 block cipher, stream cipher, which was used in the first security suite for wireless encryption web. And unfortunately, RC4 suffers from teeny several statistical imperfections at the very beginning of its output. But if you discard those first bytes, then RC4 is quite a good stream cipher. But the problem is that those teeny imperfections can be exploited to break the web. And now, so everybody knows here that if your neighbor has a web-enabled Wi-Fi access, then this is just a matter of minutes to break it. And actually, at the Europe conference, which happens now, Swiss researchers have even demonstrated that you just need 9,000 packets, and it is 3 times as less as before. So you just need a few seconds to break a web secure. Just because RC4 was not the good algorithm at the problem. It's not just, and it is RC4 is not a broken algorithm. It's just an algorithm which has some small imperfections. MD5 is used everywhere on the internet in many applications. And basically, it's a hash function which allows you to compute the digest out of some data. Unfortunately, MD5 was severely broken in 2004 by a Chinese professor. She was able to exhibit collisions, and now we know more and more how to play with those collisions. And for instance, this is also Swiss researcher, or maybe researchers working at TPFL. They showed how to forge certificates which have different properties. So basically, they were able to exploit those conditions to do some fun stuff. So another stuff that might go wrong is the bad choice of protocols. For instance, if you are familiar with the IPsec, protocol which is allows you to set up DPLs. So IPsec allows you to set up several different security configuration. You can encrypt, you can authenticate only, or you can encrypt and authenticate the communication between two IPsec points. Unfortunately, it is well known that in general in cryptography, when you only encrypt and you forget to authenticate, then you are going to lose all your confidentiality. And actually, we know now very practical attacks which allow us to break IPsec encrypt only node. So if you have some encrypt only node configuration, so just run and change it, it's not a good idea. So another possibility to go wrong with crypto is to have two small keys. That's well known. For instance, you still find many TLS cipher suits which are too weak. For instance, as soon as you have the keyword export or the number 40, like 40 bits, or des, simple des, then most likely you will suffer from some insecurity. For instance, you can buy such a device for about 10,000 euros, which allows you to break a desk in a few days. It's just a lot of FPGAs put in parallel. Breaking algorithm is a very, very hardly disabled task. So it's quite easy. So today's 56 bits can be broken in a matter of days, maybe even smaller if you have a high level. Another example was the case of the Texas Instrument calculator. So there is a whole community like to hack its calculators, and basically Texas Instrument secured the software of their calculators by implementing a kind of secure boot, but it appears that they were using the 512-bit RSA, which is a very small size for RSA, and nobody knows how, or yes, we know how. The private key of this kind of RSA key appeared on some hacker forums. So if you would like to see, you see that some lawyers went before me in there. But anywhere, you have the factors which are engraved here in the case of the calculators. But more importantly is that the guy described how he broke this 512-bit RSA key. He's not a cryptographer, he just went on the internet, he downloaded some factorization code that he did not write, he put in the input parameters in it, he just pressed enter, he waited for 73 days on his own quad-core computers, and at the end, he just had the results. So, at my knowledge, it's the first example of a 512 key RSA key broken by somebody who does not understand anything at cryptography. Okay. Usually, breaking RSA is a very complicated task for mathematicians, and it's very technical. But now you can find some software which was written by skilled people, and you can just run it on your computer. And even if you don't know how it works. There is many other examples when cryptography fails. Land manager hash implemented by Microsoft. So if you are using rainbow tables, you can break it in a matter of minutes or so. When you are using RSA, you are going to have a very dangerous job. For instance, encrypting a small symmetrical key without padding and with a small exponent is quite funny. Signing without any method pre-processing puts you in trouble as well. I won't explain why, but there is many dangers. So, and I could name many others. So, fortunately, we know correctly designed and properly analyzed primitive, and we know which key lengths are usable, are reasonable for progress. For instance, here, if I look at this list of primitive, then AS is a quite good solution. SHA-2 and the forthcoming SHA-3 hash functions are very nice. If you are using RSA with the RSA OAP for encryption and RSA PSS standards for signature, then you are on the safe side, or in theory at least. You can use elliptic curve-based DPLMAN, so there are many good standards, and when you know them, then at least you won't do a mistake by using cryptography. And for instance, the TLS security protocol is also quite a good solution. Okay. So now we can ask this question. As a developer, do you have any chance to stay on the safe side? And this is my answer. It's not that easy. Okay? Let's speak a bit about sidechain attacks. But first of all, I would like to describe three types of adversaries that we consider in cryptography. First, I would like to speak about black box adversaries, and this is the usual definition of an adversary for theoretical cryptographers. So theoretical, I mean the ones who don't use the computer but do email and writing papers using data. Those adversaries are nice guys, like this. Okay. So those adversaries just obey the rules which the cryptographers are putting on them. And basically, how does it work? As a cryptographer, I'm going to model my algorithm, my protocol, my system as a set of oracles. And an oracle is just an adversary that obeys the rules. And I'm going to interact with those oracles. I'm going to define how. Maybe I will just give ciphertext to the guy, or maybe I will give him some non-plaintext ciphertext. Maybe I will allow you to choose adaptively or not plaintext ciphertext, but nothing else. Okay? And the nice guy here will obey my rules. And then I will be, as a cryptographer, I will be able to prove mathematically, in a very complicated way sometimes, that my algorithm, my protocol, my system is secure if the underlying cryptographic primitives are secure. So for instance, we know very strong mathematical proofs for RSA OAP or RSA PSS. Well, you can say if somebody is able to break, so a black box adversary is able to break one of the two primitives, then he is able to factorize those kind of numbers, which is supposed to be impossible or infeasible. That's crypto academic crypto. Let's put it like this. The problem is that there are other types of adversaries. And a bit stronger adversaries are gray box adversaries. So, of course, there were adversaries that were not foreseen by the theoretical cryptographers. And they can interact with the cryptographic primitives in the same way than before, but they also might have just a bit more information about the computation. We will illustrate this later using the demo. For instance, the time it takes to perform the computation, or maybe we'll have a bit of information through physical leakage, current leakage, electromagnetic leakage, or maybe we'll be able to just perturb the computation and see what happens when we perturb the computation. So this is what we call side channel information. So information not coming from the proper interaction with the primitives, but information that I got with another channel. If you are playing poker playing, say that it is a 10, if the guy in front of you just becomes big red when he has a pair of ace, then you know he has a pair of ace and you can adapt to it. And there is even stronger adversaries, which are the white box adversaries. Those guys are just the guys playing the game, so they exist. That's the real guys. Of course, that white box adversaries are the adversaries that most cryptographers just do not want to hear about. we know very few scientific results on proposing security against this type of security. So they can just do everything when they want. They can complete reverse engineering the software or the hardware they would like to work. They can read, write all memories, including the ones containing keys, for instance, and they can perturb all computations. And those kind of adversaries are the ones who breaks crypto computation today, most of them. Okay, but let's come back to side channel attacks, to gray box adversaries. So I mentioned before timing information, physical linkage and faults. Very quickly, timing attacks were proposed by Paul Kocher about 15 years ago, and he showed that if an RSA private operation is dependent, is correlated with the value of the private key, then you can model this population, compute the time it takes to perform the operation, and just recover the private key. And he showed that at that time, reference RSA recommendation was subject to some attacks. Now we know basically how to protect against quite well against this kind of attacks. Another example of timing attacks were cache attacks, where you have an AES process encrypting something on the CPU and a concurrent process which crashes the cache. And each time the AES process just would like to access a subkey, then it will then perform a cache miss, and the concurrent process will just analyze where the cache misses are located and gain some information about the key. Here one knows that in less than a second you can recover the AES key. That's 65 minutes, much better. So that's another interesting story. And we have attacks based on physical leakage. As a matter of fact, so it's a physical fact. As soon as you compute something, then you must consume some energy, being software and hardware. And if it's possible to measure this consumed energy, and if this energy consumption is dependent on your secret value, then of course you are out. So this is a typical setup of simple power or differential power analysis, which is used to assess the security of smart cards, for instance. So you just speak with the smart card, you make it compute some crypto operation, you record the power consumption of the smart card during the operation, and then you can extract most of the time, if the smart card is not quite a lot of information about some secrets. This is an example of electromagnetic analysis, where you just put a small antenna near your hardware module, and you try to correlate electromagnetic emanations with your secret value. And you can, this is really useful to recover secrets in tamper-proof hardware. Now, the last theoretical stuff I would like to speak about is fault attacks. If I consider the following piece of code, which can be used virtually in every secure boot implementation or every authentication implementation. So if you are just writing something like, if the signature is okay, then I'm going to do some critical operation, else I'm just returning an error status. Basically, if you combine it, you are going to obtain in machine code something which is very similar to this. So you have a comparison somewhere and a jump which depends on the result of the comparison. Now, if you are going to be able to fault your computation, then you will notice that the whole RSA signature verification, being with large keys and a very secure algorithm, we just rely on the fact whether this instruction here is properly executed or not. So a whole RSA signature security just depends on whether a jump not equal instruction is taken or not in a proper way. So if you are able just to transform in some way the jump not equal by jump equal, then you will be able to give any wrong signature, but your signature verification process will just go straightforward, and then you have one. So how to reduce faults? basically, we know now for almost also 15 years that this crypto implementation are subject to this kind of fault. So typically, you can use here a laser. So you are going to send a laser beam on your hardware, and if your hardware is not properly protected against fault attacks, then you will be at risk. Here I have what are called glitchers or unlockers, which are well used in the pay TV tracking industry, and they are just injecting small spikes of current which perturb the CPU, the execution, which can just induce a node operation instead of a jump or something like that. And it was used by for almost 10 years to break smart card, pay TV smart cards and this kind of stuff. Okay, now let's go to side channel applied to software, and I'm going to speak about CBC padding operators now. So just a quick reminder about CBC. So when you are going to encrypt data, so you're willing to bring some confidentiality in your product, then you are going to use a block cipher most often. The problem is that your block cipher, if it, for instance, is hyperless, will be able to encrypt chunks of data of 8 bytes. If it's AES, it will be 16 bytes at a time. And of course, you are going to encrypt data of arbitrary lengths, which are not necessarily a multiple of 8 or 16 bytes. So what you can do is to use this kind of chaining mode, which is cipher block chaining, which is the one which is mostly used. And so what you are going to do is to cut your plain text in several pieces of the same length, of the block length. The first one, you will store it using an initialization vector, which is something random but not secret. You will encrypt the result, get the first ciphertext block, and then you will chain this by storing the second plain text with the first ciphertext block, and so on. And to decrypt, you do the same in the reverse order. So you will have a ciphertext, you decrypt it, you store it with the initialization vector or with the preceding ciphertext block, and you get the plain text like this. Okay. Now, of course, I said that the CBC mode requires that the data have length which is a multiple of 8 or 16 bytes, depending on the size of the block cipher. For instance, AES is 16 bytes and TS is 8 bytes. And of course, you will have a problem, a very basic engineering problem. If I have a slide with the wrong. Okay. A very basic engineering problem. You will have to pad your data such that they fit a length which is a multiple of 8 bytes or 16 bytes. So how to do? A standard way to do it is, if you are missing 3 bytes, you will just add 3 bytes to 3. If you are missing 7 bytes, you will just add 7 bytes to 7. If you are missing 0 bytes, you will just add a further block, which is consisting of all bytes to 8 bytes if you have the case of 5 bytes. And now, the problem is that if the padding checking routine is not time constant, then we know an attack, a crypto attack, which was the first time that this kind of oracular attack was proposed, and it is still a Swiss attack. So Swiss people like to break crypto, of course. And actually, this was a bit more in fashion 1 year before, when somebody found out that this very old attack could be applied on the ASP.NET framework in order to decrypt secure cookie and secure state variables. It was quite nice to see that even 10 years or 8 years after that, you still find padding in the world. Okay, so how it's going to work? Here is a way to attack a padding operator. So this is a block that I would like to break. Okay? I would like to know the value of the decrypted stuff. I don't know the key, of course. And what I can do is just try to play with the preceding ciphertext. Okay? I just here I forgot about the first byte. I just take the least significant byte, and I'm gonna to brute force it. Okay? So first value will be 0, and here if I apply the XOR, I will have a 77, and the last block, the padding checking routine will just not accept this because it's not a valid padding. If I know whether it's a valid padding or not, then I have some information. Why? Because sometimes, for one of the values here, the implementation, the operator, can say me it's a valid padding. And then, with high probability, I know that this value is the one. This one I know it, so I know I am able to compute this value here, which is the decrypted value. And then, what I can do is to fix this byte here to 2 and to brute force the second byte there until I get a proper padding. And in that case, I know that this byte here XOR this byte here is the second byte. And so, of course, I have promised to do demo. So I have here I have a padding operator. So it's a small web application which takes just 24 bytes hexadecimal strings, which is an IV plus 2 encrypted blocks. And basically I can play with it a bit. So if I launch the operator. If I play it, maybe he will say there is an invalid length. So here I have not a multiple of 8 bytes. If I put a proper ciphertext, he will say, okay, the ciphertext was decrypted successfully. Of course, he won't give me the plaintext, but he will just say decryption okay. And if I modify maybe a bit the ciphertext, he will say, okay, I was not able to decrypt the ciphertext. And now, if I have as an attacker this information, so it could be through timing, it could be through analyzing the power consumption, it could be to looking at the log messages if the application is a bit too verbose, then I'm going to be able to break this. So here, in 73 lines of Python, with a lot of comments, so it's no more than 20 or 30 lines of Python, I'm just going to brute force this oracle and to decrypt this ciphertext blocks here. Okay. So what I'm going to do is to build queries of 24 bytes. The first 8 bytes block I don't care about, and I'm going to use the second block here. The second block will be my perturbation vector here, and the third block will be the block I would like to decrypt to make the oracle decrypt. Okay. So I'm just having a loop on the 2 blocks. I'm just defining the perturbation vector. Here I'm going to put an array where I'm going to put the recovered byte. Then I will loop on each byte of the second block, starting from the least significant byte to the most significant byte. And I'm gonna to make the least significant byte, for the attacking byte, loop over all the 256 value. And what I will do, just will send the queries to the oracle, sleep a bit because otherwise it's too fast. And if I get the message, the information successfully decrypted, then I will be able to say that the decrypted block that I don't see has a 0, 1 in the least significant. And then I'm going to recover this information and compute the next perturbation vector and so on. So let's have a look whether it works. So here you have the logs of the oracle, and you see that it receives brute forcing queries. So I'm just following up. I have also already decrypted 2 bytes here, and you see that the bytes are just rolling here until I get the successfully decrypted message. It takes some time. It's a very deterministic problem, but then I am able to recover byte after byte decrypted ciphertext works without knowing the key, without stealing the key, without spying on the key. So maybe I will just put it a bit faster, and you will see that it goes 20 So in average, it has 2 times 128 queries, so that's no more than 1,000 queries. And you see that one block after the other, one byte after the other. If I get this information, I am going to recover the whole plain text, which is 2 bytes here, and that's it. Okay, so that's really an example of side channel attached to the software. It's quite useful. No, it's quite fair. Okay, another example of the same types of attack is not against a symmetrically primitive but an asymmetric one. It's against the proven, securely proven RSA-IP. This attack was also published approximately at the same time, Crypto 1, and that's already 10 years ago. And of course, at the same time, you will transform the bad implementation into a decryption oracle, and you will be able, without knowing the private key, to have only about 1,000 queries to the oracle to decrypt a 1024 RC. So the only required information, it does the decrypted ciphertext has a more significant byte equal to 0. So this is a very complicated RSA-IP scheme, but the only thing we need to know is whether this byte of the plaintext is 0 or not. So it's a simple check in software. And if I have this information, this byte is 0 or this byte is not 0. So this information I could obtain it through error messages, timing, or anything else. Then you will be able to decrypt any book. So now let's have a look at the OpenSSL implementation. OpenSSL, everybody knows about it. It's a reference crypto implementation of crypto algorithm which is used almost everywhere. You look at the changes, you can see that radically the developers were quite professional. They took into account this attack. So we were careful to secure it against JSON attack. Now we can go a bit further and to see how it is really implemented. And basically, we see a comment that signaling the 0 immediately after connection might allow for side channel attacks, etc. So the developers were very careful not to give information. The problem is that when you look at the code, you see that here you have a test. If the first byte or the most significant byte is 0 or not, then you do something or you don't do something. So there is a difference in the computation. And basically, we know that in crypto, having such computational flow difference depending on secret value is not a good idea. So the question that one can ask is that time constant? So I just propose to try. I have a small demo here, a small code which just checks, repeat a padding check, OIP to a padding check with 0 byte as the most significant byte and with a different 0 byte. So it's very tiny. Okay. 100 lines of C, no more. I can value. I'm just going to open this cell. So that's interesting. When I repeat the test as something a lot of time, I already see a difference. And it's funny because it's always the same kind of difference in the same direction. So most likely here it is not time constant, even on a very fast 2 GHz CPU. Then what you can do is to do a bit more stats. And basically you will see that the distribution it's not always. So you can clearly differentiate the two behaviors. So now the question we can ask is, OpenSSL broken with respect to envelope attack? So on the high-end servers desktop, most likely not. Why? Because if you like to attack to exploit this timing difference, we'll have to sample too many times to remove the load. So in theory, yes, it is broken, but in practice, the number of measurements will be too high, most likely, due to networking, mainly latency, or the interaction with the OS, with the TCP/IP stack, and so on and so on and so on. But the problem is that if you are going to use OpenSSL on embedded platforms, so on a device like this, which you can have in your hands, or on a USB dongle, or any small, or maybe on a game console, then yes, definitely, you will be able to decrypt any RSA or encrypted blocks. Why? Because in that case, if you have the device in your hands, you will be able to do clock cycle accurate measurements, just by doing simple power analysis, for instance, or something like that. And even if it is time constant, if the flow of instruction that you are going to execute is different, then you will be able to see it on the forward trace if you and then the platform is not protected against this kind of things. So here, even the OpenSSL code, even if it is quite well protected against this attack, it is not 100% protected. It's a bit of a pity because the OpenSSL developers don't find useful to go a bit deeper. Also, OpenSSL is used in many different, not only on high-end servers, but also in much more embedded platforms scenarios. But remember, at the very beginning of my presentation, I said usually it's not necessary to break crypto because there is a lot of other kind of vulnerabilities in products like memory exploitation stuff, or buffer overflows, or code injection stuff, and and most of the time, cryptanalytical attacks, being theoretical, practical, side channel, are quite difficult, expensive in time to mount, or maybe just infeasible. Side channel attacks are a bit difficult, but they are most of the time feasible in this case. And if you are really a lazy boy, as most people which break systems, what you do is just steal the plain text. Of course, if you are going to encrypt, sometimes the plain text will be available through another channel, or just steal the key by looking at the memory. The most famous example is maybe the SCS scheme, which is used to protect Blu-ray discs. You know that Blu-ray were broken about 4 years ago. Also, the protection scheme is a very well-designed scheme in terms of cryptography. So the cryptographer, which looks like at the ASCS specification, will just say, "Wow, they did not do any mistake." But that's good. The problem is that at a certain moment, when you are going to decrypt a Blu-ray disc, you have a key, which so we can recover that key with a very competitive way. But then you have to use that key to decrypt the content, and this key must be stored in memory. Okay. So what did the hackers? It's just they took the WinDVD software player, they found the address in the heap where the key was, and for each Blu-ray disc you just steal the key, you decrypt it, you put it on the internet, and ASCS is the one. So that's really how it is doing in practice. You don't have to put Python and to do very complicated stuff using it. So, conclusion. Most of the time, you can break crypto without doing any cryptanalysis. Most of the time, if you have maybe a slightly too short key size, this does not matter because there is many other ways to break this code. And the security of a crypto implementation is often another topic. time people don't think about it, but it's one of the weak points of cryptography that can find in the network. That's it.
Yeah, so we have a couple of minutes left for question and answer sessions. So please direct your questions now. Please wait next, please.
No. I'm not very familiar with this.
They also use the test line to get back to the...
I'm not very familiar with this.
There afterwards so when it's accidentally made itself and hardware encryption.
Of course, you can encrypt the memory. To encrypt the memory, you need a key. Where do you put your key? Now, of course, it's possible to design systems which are very secure, because you are relying on trusted hardware. Of course, you can make every system in hardware. But if you will also have real, for instance, in PlayStation, it's quite well designed. It was really difficult to break it. Now you know how to break it, you know how to recover key and it's called. But it is really a mix between first the hardware and very small elements of the world code which you can identify, which checks everything, and then software which is kind of protected by hardware. If you consider the TPM chips that you have in PC, you can also think about relying on keys to do some security. But if you got it, so 100% security.
The PlayStation you just mentioned, that also involves the cryptography.
Oh yes, that's right. I have forgotten it. They just misuse the ECDSA algorithm. So when I teach ECDSA to my students, I say, when the ECDSA asks you to draw a random value, please draw a random value. Please do not put a constant. Of course, Sony developers did not follow my lectures, and they put a constant value. And in that case, you just have to do a bit of mathematics, recover, and it's particularly annoying in the case of ECDSA because you recover the private key directly. So it means that here everything. It was thank you to remind me, it was a very nice error, a classical error. Yes?
I think the whole topic for the last few months is maybe the cat and mouse game between Gamecom, the digital TV encryption, and the e-box and the
Okay, I must stop you here because I'm on the NDA for all this stuff.
Sorry?
I'm on the NDA for all this stuff. So I'm still working with the company doing the cable condition access system, which is previously but yes, it's a funny cat and mouse. And just to know that the system with my cable phone is almost 12 years old. So, any other questions? Please, hear the noise. Who is the most powerful adversary? Bruce, a white box one, gray box one or black box one? I guess what would be the majority. Okay, well, there is not a lot of blues, of course it's a white box that is So next question. Oracle attacks can be exploited through timing differences only, false attacks, timing differences and error messages among users, or the use of a Boolean laser.
I had one.
And of course here the answer is C. Most of you are not sleeping, that's good. James Monger is a well-known writer, is the father-in-law of Barack Obama, is a well-known because they have and once managed to write a nice paper. Of course it's D. And for the record, it was quite funny because at the same session at Crypto, you had scientists presenting the security proof of RSA OLP. So a very involved mathematical proof by the best minds here in the world. And just 1 minute later, you had this guy, James Monger, showing that, okay, but if I just know whether the most significant byte is 0 or not, I can break it in a second. So you are reading the two words of crypto which were in fact one word. It was quite interesting. I will remember this one. And last question. Are usually not vulnerable to oracle attacks, are usually not vulnerable to fault attacks, are usually vulnerable to such attacks. I'm not interested for Of course, the C1 is. Thank you very much.